fly the older space shuttle and leave it on orbit and build on it. And the international partners looked at that and said, oh my God, this is ridiculous. So anyway, but this was a time when we thought that the whole program would be canceled because we ran out of money, basically. We promised the station for $8 billion. We'd spent $8.5 billion and hadn't built a single piece of hardware. But then the Russians came in and funding was, and the Europeans and Japanese gave more money. And so we ended up with the current design. This is what it looks like on orbit right now. So this is Expedition 56. This is the 56th crew to man the space station. And so we have a NASA commander, but in a couple months, Alexander Gersh will take over as the ESA commander, European commander. And so we have Japanese station, a module here, European module, US node, US lab, US node, and then the Russian side, the Russian FGB and the Russian service module, which is basically a copy of the mirror control modules. And then you see some of the docking systems with the Soyuz, which carry the crew, and the robot vehicles, Progress, that deliver supplies from the Russian side. And there's also a commercial inflatable module test here. And there's my little tunnel. So this is a assembly sequence, runs a minute or two, and it shows all the different parts. You can see that there are two versions of the tunnel here. And so this is the sequence. It's almost the 20th anniversary of the first module, first part launched in November. And you can see that at this point, you start having a crew on board. And so from here on, all the assembly activity has, like most of this is delivered by a shuttle coming up and docking and delivered, but now the robot arm on the station is helping assemble parts. And what's amazing to me is that all this is being done without windows, basically. I mean, you don't see very well what you're doing. You only look at it with robot assembly through the TVs for the video screens. I thought that, in our design, we launched the window module early on. Somehow it got pushed to the very last. And so somehow they decided they could, the astronaut office decided they could do it without the windows. So there's the thermal radiators being added. This is the European module. This is the Japanese logistic module, Japanese module, now the biggest. Adding the final solar arrays. There's the external platform that the Japanese. And logistics carriers, external payloads. They're moving the tunnel again, moving it for node 3. There's the window finally arriving. And then the Russian research modules. Another surprise was the need for storage for so much, because they finally decided to leave one of the logistics modules on there just for extra storage. And this is that was basically the configuration. So the robot arm, where did the arm go? Oh, here it is. It's sitting on this track, and it can actually move back and forth along this track, and it can hop end over end like an inchworm across and walk across the modules. So it can be controlled every time it unplugs from one side, it's plugged in on the other, and it's being controlled, hopping over end over end. Their astronauts can control it like that. They can also control it from the ground. And so typically they'll set the robot arm up. Actually the robot arm's down here. They'll set it up to whatever it's going to do for the next day. Then the Japanese have their own robot arm out here. The Russians have one back here. Any other questions about, well, we have this picture up, yeah?
How long did it take to all come together?
Yeah, so it's, there are still parts that are, the Russians still want to launch some parts, so that it's been 20 years. And so the last, I mean, like I think a year and a half ago was the addition of the Bigelow expandable inflatable module. And so, and they're still talking about adding another node out here, and I'll show you later that some commercial companies want to add parts out front here. Yeah.
Would it be safe to send that to Mars, to orbit Mars?
It's possible that this configuration would work in Mars orbit, but it's going to take. I worked on a couple studies about sending it to the moon, and basically it's you need about 3 or 4 times the weight of this vehicle in propellant to blast it out that far. And so if you just picture, launching, right, it might be possible in the future and people have talked about taking off pieces and sending it to the moon or Mars. But it's just very difficult to leave Earth orbit with this big mass. So if you, but yes, it theoretically it could work around the moon and Mars, same kind of thing. It's when it's there's not too much that's designed specifically for Earth. When it orbits, it's coming in this direction at 8 kilometers a second, and the solar rays keep facing the sun, so they're rotating backwards, flipping around like this, in order as it orbits around the Earth, so that these things always face towards the sun.
Eric.
Oh yeah. Another question? Oh, sorry.
Just a quick one. And look, I saw a lot of reconfiguration of the design of the architecture. How long did it take to come up with a really sort of stable design with a lot of fidelity?
Yeah, it was pretty well set. Basically, there were so many redesigns of, like 5 years worth of redesigns but about another 4 years and the design was pretty stable. However, there was a lot of flexibility. There's all these modules, the interfaces between the modules, you can move them around, and so a lot of the choices, like the addition of node 3 here, was decided much later. And so that was not part of the original design. And the Russians are very good about always having their nodes be completely interchangeable. On the US side, they tend to get we got a little lazy and said, oh, the airlock is always going to be on this side. So let's make all the tubes for the airlock only in this spot. And so you can't move the airlock. But you can move some of these other parts, like this thing can be over here, and that can be moved over here. And so you can, so there was some flexibility in that part of the design. The truss ended up getting completely set, in 20 years ago. And there's been some designs about, adding more power out there or adding a lower keel, but that's never gone anywhere. Yeah?
Would it get blown away by Mars's biggest storm?
With there are moons around Mars, but you can avoid them if you choose where you orbit. And so you orbit underneath the Mars moon. So all the parts on the US side were brought up by the shuttle. Here's its part bringing up the Japanese logistics module and the base of the arm here. And so this is, you have the shuttle docking up front and the Russian, the shuttle Actually, the Japanese HTV was grabbed by the arm and gently attached to one of the node connections. But the HTV and the European one and the Russian ones all dock, by basically slamming into the docking port and having the latches click. What's one remarkable part is, actually I'll show it back here, this area. The US actually adopted the Russian design for the docking port. So that was about the only case I've seen of the US completely throwing away the design they were using and using the Russian. Because it was on our tunnel. So, yeah, go ahead.
I always wanted to ask this question, so please answer me. How do you, for example, the oxygen inside that place, how do you produce oxygen? Like, is it tubes? Like,
Yeah.
How long an oxygen can continue being?
Yeah, and so there is actually a mechanism for converting extra water and splitting it into hydrogen and oxygen and producing extra oxygen that way, and then venting the hydrogen overboard. And so, so mainly everything is dealt with the water supply, and whether or not you have enough water supply, both for everything you need for water and then also for oxygen also. It's a little different than on the Russian Mir station, for example. They had an emergency system that would produce oxygen with a chemical reaction, and they had one problem with that. They had a fire in that, so the U.S. sort of shied away from the emergency oxygen provision. They just wanted to use water systems.
So if they run out of water, no oxygen.
That's right. Yeah. Yeah.
So we're going to keep shipping water up?
They ship water up, but they also, they ship water up to replenish what is a 95% closed system. And so it's another example of a change in technology. They used to have 2 refrigerator-sized systems that would purify the water, and now it's done by reverse osmosis in a little bag about that big. And so it's a remarkable technology that allows you to purify water. And in fact, people who made that also make a version of a backpack where you can have a little water spout, and it has attachments down here. There's like, anyway. So if you're walking in a desert and you absolutely need water, you can survive.
Following on that, what happens with the carbon dioxide? Is it decomposed or vented or?
Yeah, they have another process to scrub the carbon dioxide, and I don't remember exactly which process they use. I think they've changed a couple times with that. They used to just collect it capture it chemically, but now they actually put it into another system and break it back into to oxygen, and it takes a lot of energy to convert it. So let's see. So here they have, this is the empty bay of the shuttle with the part of the robot here. Here's the Soyuz coming in, docking, slamming into with its docking system. This is the only way to get to the station right now. The 3 astronauts sit in here, and they use this module. If they take, there's a slow and a fast way to get to the station with the Soyuz. A fast way takes 6 hours. The slow way takes 2 days. And so if they take the slow way, they live in that little tiny module. Here's the window, the cupola, which is facing down toward the Earth. This is the you can see that we're opening up the orbital debris and micrometeorite protection shields to use it. And here's one of the U.S. Logistics modules, the Cygnus one, which is being grabbed by the arm and then berthed. And then this is the Dragon. So this is the logistics version of the Dragon. The crew version of the Dragon is going to look very similar, and it is being tested at, next few months, and then hopefully fly crew next year. Yeah, and here's the example of the Japanese module, which was so big that it had to be launched empty and then be outfitted on orbit. He's actually playing around because you can just move these half-ton things with a finger. But yeah.
So how long are these particle absorbers left open when you look into those windows?
Oh yeah.
Is it
Well,
potentially really dangerous? As
yeah,
well?
it's potentially dangerous, but they sort of accept this as a background risk. I mean, at least it's facing down. It's not the debris comes in horizontally. The micrometeorites come down from above, so you're not too much risk from looking down at the Earth.
Is there a minimum time or a maximum time that you can?
I don't know. That's a good question. I don't know what the maximum time is. It's also probably a thermal issue too.
So how much work do they have to do to keep the station rotating so it's always facing downward?
Yeah, so it's they basically have started it spinning, and it's in the local, vertical, local, horizontal. It will continue around like that. If it's only you know, like when something docks or when they fire the reboost jets, that they actually get a disturbance on the. They have to then correct on. But they have these giant gyros, you know, half-ton gyros that are spinning that will, you know, can control the attitude of the station.
So they have to stop it when they're boosted up and then they spin it again?
Yeah, they're still, the spin rate is so slow, you know, like, it's like once every 90 minutes, and so it's, so they can boost while they're in that attitude and rotating slowly. Yeah. And here they are assembling the truss. You can see New Zealand back here, Christchurch and Wellington.
That's so cute, that picture. You should have used that picture.
Yeah, no, we've used this one a lot, yeah. And here's an example of them gathering in Node 2 to watch the movie The Martian. And then looking out the window, this is in the Russian side, looking at, you can see a couple of cameras, ordinary camera and then a big telephoto lens. This is sort of what you see with the ordinary camera looking at San Francisco and then the telephoto lens. So this was a failure of our imagination when we worked on the design 20 years ago. And we had no idea what it would actually look like. So I've included in that folder these links. The virtual tour is an interesting one. It allows you to move around on your own inside the station. I was going to try to play a couple of these, maybe a fraction of a minute on this. Let's see. So this is, oh wait, I forgot I didn't plug in the audio. No. Oh.
Touch the wall. What I like to do is I just have it attached here, one point and one point up here, so I can put my feet right up here.
You showed me this
on
PS3
kind in the sense of this position, like this, and I kind of curl up a little bit in the semi on my side sleeping position, so I can be back on Earth. And it kind of works out pretty well. It gives me the same feeling, almost, but it works well for me. And then when you wake up in the morning, the first thing you see is your laptops. I got one that connects to the internet, which works like 50% of the time. And then I got another one that does our LAN up here, which gives us our schedule, all the other information, our email, everything we need to do to work up here. And that's what that one is. And we also have an iPad, which as you can see. And that's also up there, and that's, again, for all sorts of work or for watching movies or something like that. That's what it's good for. You know, it's actually not a bad setup. I know it's small, but really, it works out well. We don't really need much more room up here.
What you don't see until later is that there's a one above and below.
Let's now move on to the lab.
So this is
Begin to look on here. So what we're doing right now is we're heading towards the back, towards the aft. We were in the very front, in the middle. Now we're going down this long path on the back. The first one we come to is the lab. And you see on the back, on top of the lab, I should say, the very aft part is this big structure over here. It's called this truss. Sorry.
Let me jump ahead a little bit.
We have a
He's opening up the robot here.
So he's been running this project. We've been upgrading all the electronics in there, the computers, etc. And then this next week I actually get to put lights on it. I think it's going to be actually kind of creepy looking when he gets the lights. But hopefully it'll help him walk around the station, move around the station. And as you look around the other spots, then we have on the top, we call them express racks. The express racks just means really it has power and data for any kind of experiments that want to go up there. So anything on the ground, somebody comes up with an idea.
You can see the tangled wires.
All they need is a data connection and power. They can design it to fit in here, and we can easily put it on there, hook it up. And
they have a whole army of people trying to keep track of where the astronauts put things.
Check the works out pretty well, because we'll set it all up, and they can run a lot more sites that way. So if we move to this way, of course, we got the bike here we set up for it.
And let's see. Let me jump ahead. That's there's for example the airlock with the on the U.S. side with the two spacesuits, and you can see that the airlock is all full of storage. They run out of storage locations, so even the airlock is. And so it does worry me that they won't be able to do a fast EVA because they have to unpack that whole thing. So if they ever get a puncture and they have to go outside to fix it, they're going to be slowed down. Then I wanted to show you a little bit of this, which is the this is the toilet. You're going to be curious about it.
A green little system up here where we recycle quite a bit of all the fluids that are used up here, I guess. Condensation or sweat, everything, it's all sent back into the system and we're using it. So for the bathroom, you know, they call the bathroom the can. There's a reason why we call it a can. Because here it is right here. There's a can. That definitely is a can full of crap, literally. So that's what happens. You can sit here when you want to use it for that version of it. It makes you use a little bit of suction that comes down there to help keep pretty much the smell from coming up and everything else from coming up when you're using it. And we use little packets here that fit into a hole that fits on top here. These packets go in here. You use one of these packets, of course, and when you're done with the packing, you wrap it up and push it back in there. About every 8, 9 days, that becomes full, and we put a new one in. That also can send throw down in the PMM for our trash, and hopefully on our cargo vehicle, it's all done. It's going to burn up on the way in. You put those on there and it's done. For urination, you got to go there. First, it's white, yellow. It's a standard. It's a suction. Basically, there's almost like a wet back in the back here. The way I look at it. And so it separates the suction out of it.
And then what's funny also is that the window is right next to the toilet. So the best view of the Earth is behind the toilet.
And there's a beautiful Earth. So you can hang out. You see the arm? I don't know if you can see the arm there. It's set up. It's on the top, or sorry, on the bottom of node 2. It's connected to it right there. And that's the position we use to grapple the cargo vehicles, SpaceX and Soyuz and these.
I'm going to go back to this. So, oh yeah, go ahead.
How much time do astronauts have for themselves? For sleeping.
It's been set up, they finally, they tried everything, but they finally settled on almost like regular weekday kind of schedules where they basically work for 6.5 hours each day, which is because they have a long period of time of meal time, and they always have 2 hours of exercise every day, and they have, after waking up and before going to bed, they have their own personal time. And then they also have the whole crew on one schedule, which is Greenwich Mean Time, basically, England time. And so all the different control centers in Russia and Europe and US and Japan have to accommodate that schedule. So they do Russian activities in the morning and major US activities in the afternoon when Houston is more on normal time for Houston. That's the biggest difference. If you go as a tourist, you actually can sit there and look out the window, and the astronauts are very jealous because they're all turning on switches and things like that. One thing I wanted to point out is this little thing. Some of our students from Singularity University formed a company called Made in Space, and they have two 3D printers on space station, and they're making bigger plans of assembling large structures in space, both satellites and then in the future for big space cities kind of thing. And it's all starting with tiny little things like this. This object only got transmitted by an email to space, and so it was created on orbit. And that's the future of a lot of space habitats, is that we will just send up the means to produce them and build them, and we'll just transmit the information on how to build them. And yeah, this is just a joke. I like the monkey house. And let's see. Okay, here's some of the designs. There's now inflatable habitats where you launch a core. Bigelow in Las Vegas has several space stations waiting on the ground to launch. He's just been waiting for the crew vehicles to be ready to service them. So you launch one module and it expands out with these Kevlar kinds of bags, and it becomes a big volume with just one launch. And here's the crew vehicles that he's waiting for. Starliner and Dragon 2 are going to be hopefully flying next year.
The Bigelow one, is the shielding on that better than what the current space station is?
It's similar. They've actually flown for more than 10 years, been flying 1/3 scale test models that are up there. And so they've been demonstrating that there's no pressure loss or anything like that. And so it's real similar. It's about 7 different layers of material for pressure and for meteorite protection. And then there's also some various people have been trying to do space hotels, and there's also an Axiom company that wants to add a module up front, do my little tunnel, and then separate out and fly it as a separate space station. And so they're just started last month. There's 13 different companies are working on plans for what's the future of commercial space stations. Or another one is Orion, Aurora, with doing a space hotel. And so these are very similar, module kind of things that we've seen before. They're old concepts about, even the Japanese Shimizu Corporation had this concept of a space hotel with an artificial gravity part and zero gravity and a big disco ball in the middle that you could have a big party at. And there's Patrick Collins has been studying the tourism market, and if you get the price low enough, you suddenly can tap into the $3 trillion a year tourism market. which is so that the tourists around the world spend all the world